Hello, everybody. What we're going to talk about today is the history of observations of our galaxy, the Milky Way galaxy, and also other galaxies. So the way I want to start is this. I want to start with Galileo. It's good. We're going to talk about some people today, and I'd like you to write down these people. Galileo was the first to look through a telescope at the Milky Way and realize it was made of stars. So Galileo was the first to realize that our galaxy, this band of light that you see stretching across the sky, was composed of stars. That's good to know because he was the first to use a telescope to look up. Now, if you've never seen the Milky Way, you got to get out. I mean, I'm sure you have extra time these days, maybe. So what you should do is go out to a nice dark sky and just, especially, in the summer, hopefully things will be getting better too. Get out there. The Milky Way is this band of light across the sky. It's our galaxy as seen from inside. And in our galaxy, we see dark areas, dark nebulae, emission nebulae, but a large percentage of stars, very dense. And that's what makes that band all the way across the sky. Take a look at this. Great shot with this dark nebula, absorption nebula. And this is an area of, this is Scorpius in this area, looking in the summer to the southern area of the sky and to south from our point of view, Scorpius and Sagittarius. And look at emission nebulae and reflection nebulae. Just beautiful. Now, look at this shot, wide angle Milky Way shot. Just, there's the North American Nebula right there. Great shot of the Milky Way on a road. Wide angle shot of our galaxy, another one. Look at this shot, Milky Way from the Death Valley, nice black and white with a panoramic shot where this side matches up to this, 360 degrees, so it makes it look like a Milky Way bow. Now, William Herschel, good to write down William Herschel. He felt that our galaxy was relatively flat, and we were at the center. So this is his idea, his view of the way our galaxy looks, like a grindstone. So Herschel came up with a model of our galaxy and said that the sun was at the center. It looked like the sun was at the center of our galaxy because you see the same density of stars in every direction. That's Herschel's model. It's called the grindstone model. Actually, Herschel's also the one who discovered the planet Uranus too. So Herschel, pretty good astronomer. Even his sister Carolyn Herschel was a great astronomer too, and they were both. Well, at least William was a musician too. That's William Herschel. Now Shapley, not Shapley, but Harlow Shapley. Good to write down Shapley. Shapley. He made some assumptions here to try to figure out what the Milky Way galaxy was like, where we were within the Milky Way. So do not write this down. But what Shapley did, he assumed that globular clusters were symmetrically distributed around the Milky Way, figured out the distances and directions to the globulars, found more of them to one side than the other. So what Shapley figured out, this is what's good to write down. He figured out that the solar system was not at the center of the galaxy. Before that, we thought we were. But Shapley figured out we weren't by seeing the distribution of globulars. And from our point of view, we see more globulars in one direction than the other. If we were at the center of the galaxy, we would see these globulars in all directions in the halo of the galaxy. So if I ask you something about Shapley, Shapley was the one who figured out we were not at the center of the galaxy. We're off about 2/3 of the way from the center to the edge. So there was his distribution. Don't have to write that down. Look at this Kona Galaxy Garden in Hawaii. As far as galaxy gardens go, this is one of the top. Now, if this represents our galaxy, just beautiful. This is a beautiful, I think, this artist's conception. It's not a real shot. We can't get out of our galaxy to take this picture, but look where the sun would be. Maybe about 2/3 of the way from the center to the edge. And here's a galaxy diagram. We think that our galaxy is relatively flat. We believe it is. That's why it looks like a band of light, has spiral arms. The sun is off over here. Here's a edge on view. Here's a face on view. Here's the nucleus at the center. Here's the halo. Sorry about that. Here's the halo of the galaxy where we find the globular clusters. Here's the plane of the galaxy or the disk, you see this called the halo. That's where the globular clusters are. And they say now our galaxy is about 100, we used to think it was only about 75,000 light years across. Then I heard 100,000 light years. Now they're saying it's about 150,000 light years across. So that's, and only about 1,000 light years thick. So it's very, very long. It's like almost like a sheet of paper as far as the dimensions, as far as the scale. So what do you need to know here? We have about 200 to 400 billion stars in the Milky Way. It's good to know. And we go around the center of the galaxy in about 200 million years. It's called the galactic year. So we, as the galaxy spins, we go around the center, and it takes about 200 million years to go around once. It's called the galactic year. So since the Earth was born and the Sun was born about 4.5, 5 billion years ago, it's only been about 23 galactic years. The Earth's 23 galactic years old. The Sun's about 23 or 25 galactic years old. So if you look at it that way, it's not that old. Since the dinosaurs have died, it's only been a third of a galactic year. That's kind of weird to think of it that way. Well, here's a radio wave view of the center of our galaxy where we think maybe there's a supermassive black hole, a lot of radio waves coming from there, probably from the accretion disk. Supernova remnants we see in the distance with radio waves. We can't even see this with visible light. We can see much, much easier to the center with radio waves, using radio wave light. But visible light, we only see like 1/10 of the way to the center. Yeah, good luck with this Milky Way galaxy animation. It's not a PowerPoint, here's a PDF, so that's what you get. Hubble. Good to write down Hubble. We're going to talk about the types of galaxies. Hubble types. They don't even call them Hubble types anymore. But remember Hubble, the one who figured out that other galaxies existed? Well, how did he do it? He used Leavitt's period luminosity relation. So it's good to know Hubble, Edwin Hubble. It's always good to know Leavitt. So Hubble figured out other galaxies existed. And so he was at Mount Wilson in the Los Angeles area when Los Angeles was nicer because the Dodgers were not there yet. And the skies were also darker. I mean, not as much light pollution. So no Dodgers, no light pollution. LA was nice then. Remember, he's the one who looked at the Andromeda Nebula, realized it was a galaxy, using the period luminosity relation and these Cepheid variable stars to get the distance. Well, he figured out there are other types of galaxies. There wasn't just like spirals like the Milky Way. There were things that look like footballs, these galaxies. There were different types. They used to call them the Hubble types. Today they don't really call them that, but yeah, I don't know. It's Hubble's the one who figured this out. Well, let's talk about the Hubble types. What do you need to know? All right, first thing, elliptical galaxies. You don't have to know type E, just know elliptical galaxies. Here are some things I'm going to tell you what you need to know for these. You're not going to have to identify on a test, but you should know characteristics. So ellipticals, very little gas and dust. Because they have very little gas and dust, there's not much new star formation. Stars aren't forming if you don't have gas. And if there's no new star formation, there's really only old stars there, type K and M, the ones that live the longest, because O and B stars don't live very long, so only old, tens of billions of years old stars, let's say. Type K and M, maybe even some Gs maybe, but mostly K and M. Diameter, they could be very small, only 3,000 light years across, but they could be also, I mean, that's a fraction of the Milky Way galaxy. They could also be like 5 times, 6 times as big as the Milky Way galaxy in diameter. So no, they can be very small, they can be very big. And so here's what the main thing I want you to know. That there are big ones, the giant ellipticals, but there are also a lot of dwarf ellipticals, a lot of small ones. And dwarf ellipticals may be the most common type of galaxy. Write that down. Dwarf ellipticals may be the most common type of galaxy because they're small. Potato chip rule. Got that? So what do you need to know again? Elliptical galaxies, very little gas and dust. Means no new star formation. If there's no new star formation, there's only old stars because you don't have new ones forming. You only have the old ones there. And they could be big, they could be small, and the smaller ones called dwarf ellipticals, they might be the most common type of galaxy. It's not the most common type we see because they're very faint and very small. They're made of very low luminosity stars. Let me show you some. Well, I'll show you this M87 giant elliptical. That's where we found that black hole Well, we got that pretty decent shot of a black hole. That was an M87. It's a giant elliptical. Sometimes we call these elliptical cannibals because they eat other galaxies, and because they're so massive. You don't have to know that. Here's another elliptical. Notice the reddish color, orange. Another elliptical, kind of yellowish. Sometimes look like footballs, sometimes more spherical. All right, now, spiral and barred spiral galaxies. What do you need to know? Well, they have spiral arms composed of stars, gas, and dust. They have a lot of gas and dust. That's good to know. They have a lot of gas. It means there's star formation occurring. If there's star formation occurring, that must mean there could be young stars there, if there's stars being born, and there's old stars too. Now, if you look at it, look at a picture of one, you see the blue areas here. Those are O and B stars. So that means they must be young if they're O and B. They don't live that long anyway. A lot of the older stars are found in the center. So the star formation is going on in these spiral arms. And the difference between spiral and barred spiral, some of them have just a nucleus of very old stars, but some of them almost look like they have handlebars. You see that? This looks like where you grab it right there and there. If they were like handlebars, those are called barred spirals. So they're pretty much the same kind of thing, except we think over time, spirals, the nucleus slows down a little bit over time and turns into a barred spiral. So we think this is like evolution of galaxies. And for both young and old stars, they're more the size, consistent in size, anywhere from 15,000 light years to 650,000 light years. You don't have to know that. But a Milky Way is a typical spiral. It's actually a barred spiral. So here's something that's good to know. It's the most common type of galaxy observed. It may not be the most common type, but why would it be the most common type observed? Because it's bright. It has very luminous stars in it. And they're also pretty big for the most part, these spiral galaxies, compared to like dwarf ellipticals. So they're made of bright stars, luminous stars, and they're bigger. So you can see them from farther away. And something else that's good to know, the Milky Way galaxy is now thought to be a barred spiral galaxy. It's good to know what your galaxy is, a barred spiral. Don't worry about diameter, don't worry about mass. But again, they have spiral arms made of stars, dust, and gas. There's a lot of gas and dust, and if there's a lot of gas, it means there's star formation. If there's star formation, it means they're going to be young stars. Plus, if you see yellowish, there's going to be old stars too. Look at this spiral. Just beautiful. Spirals are the typical, like, when you think of a galaxy, most people think of spirals. Star formation, that blue right there. Those are not, it's not just reflection nebula you're seeing. If you're seeing at a distance, seeing blue, you're seeing O and B stars. You're not going to see reflection nebula from millions of light years away. So the blue you're seeing here are O and B stars. And if there's some O and B stars, I mean, enough to light it up like this, there are going to be tons more of all the other types of stars, because remember, O and Bs are not that common. So, but you can't see the other stars. They're there, but they're not luminous enough. You're going to see the O and B stars from a great distance, and you're not going to see like the G, K, and M stars from a great distance. They're not that luminous. Look at the whirlpool. Face on. Look at the spiral arms where the stars are forming. Notice what you see there. Emission nebulae. Those are places where stars are forming in the spiral arms. Look at this beautiful shot of a galaxy called New General Catalog 1512. Star formation going on right there. Look at oh boy. The tadpole, is that ruined? No, at least, yeah, with Mike Healy here, it would be ruined. But no, actually Joe left me a good shot of it. So there's a tadpole, great spiral. Look at the background. Look at all these other galaxies in the distance, except for individual stars that might happen to be in the Milky Way. It's great, a beautiful spiral. Look, it's like two galaxies colliding, another spiral there, it looks like. Andromeda galaxies, a spiral galaxy. There was a very high resolution picture of I saw it on Facebook some years ago, of the Andromeda galaxy, where it allowed you to zoom in and just a little area, small region of the galaxy, and just see how many stars are there. Just incredible. Here's that, close up towards the center of this galaxy where stars are forming, right around the nucleus here. Edge on view of a spiral with you can see if there's a dust lane right here. It's a spiral galaxy. Usually when you have a dust lane spiral or a barred spiral. Now this one, if you squint, it looks like it has some bars. It's a barred spiral. It's like a barred spiral down here too. Barred spiral, and in the distance, a barred spiral. Look at that. That's classic barred spiral. Great shot. Oh, videos to look up. If you want to look these up. And also, you know what? If you go to my links at the Astronomy Links, which is near the syllabus, right kind of on the home page, there's one site that says Astronomy Links. There's a bunch, and you go towards the bottom. There's a lot of videos. Some of them are not active anymore, but if you're bored one day, go to those links, and you can see a lot of stuff. Go to the Galaxy links towards the bottom. You can see a lot of good stuff. A lot of good stuff in there. Every topic, there are black hole links in there that you can click on, different videos. Lenticular galaxies. Type S0. Now let's talk about these. These are kind of weird. So what do you need to know here? They're shaped like a lens, kind of like a spiral when observed edge on, but there are no spiral arms. They're like a frisbee. They're the shape of a frisbee, or like a flying saucer shape. But there's no spiral arms. There's sometimes a lot of dust, but there's not gas. So there's not much star formation occurring. So that's just these first 3 bullet points are good enough. You don't have to worry about the rest. We think that lenticular galaxies come from spirals over time when enough stars form from the gas and dust, and there's not as much gas and dust anymore, and they lose their spiral structure. So we think this is an evolutionary process from spirals eventually to barred spirals, and maybe eventually the barred spirals become lenticulars. And the biggest galaxy ever seen is 25 times the diameter of the Milky Way galaxy. It's a lenticular. You do not have to know that. Here's a lenticular, edge on, some dust lane, sometimes spirals and lenticulars, hard to tell. Here's the largest galaxy ever observed, the one that's 25 times the diameter of the Milky Way galaxy. So lenticulars, especially this one, the largest one ever. And this is about 1 billion light years away. That's why it doesn't look that big compared to some of these other galaxies. You don't have to know that. Do not have to know that. Look at this lenticular. It looks like kind of looks like a frisbee kind of thing. All right, irregulars. Irregulars have no distinct shape. Kind of makes sense, irregular. A lot of gas and dust, though. A lot of gas. So there's star formation if there's gas, and there's both old and young stars. If there's gas, that means there's stars going to be forming, which means they're going to be both young and old stars. Don't have to worry about that. Don't have to worry about that. Actually, don't even have to worry at the bottom. They used to call the LMC, the Large Magellanic Cloud, and Small Magellanic Cloud irregulars, but they call them Magellanic spirals now because there's they think they detected a spiral arm. We think that a lot of these galaxies that are kind of like this come from collisions between galaxies. So galaxies collide, taking billions of years. Stars don't even hit, but they kind of messes them up gravitationally, get all discombobulated. Look at this irregular. Look at that irregular. Look at the spiral in the background. And look at this. This is one irregular, like from a collision. Here's an irregular. This is an irregular. A star in our galaxy in the foreground. Colliding galaxies. Take a look at these. Hubble Space Telescope got a view of a bunch of galaxies in the middle of collisions. Again, taking billions of years for these collisions. Look at that. Looks like 1, 2, 3, 4 galaxies colliding. Spirals. Look at this one. Galaxies colliding. Look, gas is mixing together where they're colliding. Even though stars don't hit, gas mixes together, and that's star formation. If you see blue there, it means O and B stars. Stars are forming right there, right where they're colliding. Look at that. It's like they're doing a swing dance, holding spiral arms. Stars in the Milky Way in the foreground. These stars are close, relatively close in our galaxy, and everything else is incredibly far. Great view of a colliding galaxy. Here's one called the antenna, seen in the movie Galaxy Quest. We're actually featured in Galaxy Quest. Nice colliding galaxy there. Look at these two colliding. Just great shots. Here's a ring galaxy or starburst galaxy from a collision. Just some great shots. Cartwheel galaxy, looks like 2 or 3 galaxies collided. This is actually one picture. You might say, well, what is going on here? Well, that looks like the nucleus of a galaxy. This looks like part of another one where stars are forming. So who knows what's going on here? It's from a collision of a galaxy. Here's an exercise. You don't even have to do it. You got credit for it. But if you're bored, you can take a look at these galaxies and see what you think they are. All right. Well, that's it for the Milky Way and other galaxies. Next time, we're going to start talking about cosmology. And in the meantime, take care. We will talk to you soon.